Yeah, thank you. Something like this. Okay. Well, hello, everybody. I'm going to talk about the discretization of differential forms and how to use them to solve PDEs numerically. This happens in the framework of finite element exterior calculus. You can think of this as basically being a unified framework for PDEs and the finite element method formulated in differential forms. The core idea here is basically that instead of discretizing the individual function spaces, we discretize the whole DRAM complex. And in this way, get structural preservation. We somehow respect the topology and obtain correct solutions in this way. The big theme here is going to be cohomology, which we will talk about a lot today. And I basically worked on this in the context of my bachelor thesis, which was developing a Rust finite element library that uses FEEC on coordinate-free simplicial complexes in arbitrary dimensions to solve the Hodge-Laplace equation, which we will look at now. So this is basically the PDE at the heart of finite element exterior calculus. It is basically a generalization of the scalar Laplace equation, but here our domain is a Riemannian manifold, and U and F are K-forms. And yeah, this is basically the prototype PDE for FEEC, and it underlies more sophisticated PDEs like Maxwell's equations or elasticity equations or Stokes flow. And yeah, we basically want to start by somehow defining this Hodge-Laplace operator. For this, we need to understand the co-differential. We just introduced the L2 inner product of differential forms. And the co-differential is basically just the L2 adjoint of the exterior derivative. At least on closed manifolds. If we were to have a boundary, this would basically give rise to a generalized integration by parts formula for differential forms, where there is an additional boundary term. And yeah, in R3, for instance, we can look at these adjoint relations. So on the left, we have basically representatives of the exterior derivative. On the right, co-differentials. And so the gradient and divergence are adjoints of each other up to sign, and the curl is self-adjoint. Then we can look at the scalar Laplacian. So the scalar Laplacian is basically just minus divergence applied to the gradient of u. The gradient here is the exterior derivative, and the minus divergence is the co-differential. So the scalar Laplacian really is just a composition of first exterior derivative and then co-differential. The full Hodge-Laplace operator features both permutations of these compositions of operators and stays within the same degree by first either lowering or first raising and then doing the opposite. And basically at the two ends of the DRAM complex, we only get to see one part because at zero forms, we cannot lower degree more, so this part drops. And at n forms, where n is the dimension of the manifold, we cannot raise it, so we lose the other part. Only between we get both parts. And basically in R3, the Hodge-Laplacian always lives. Basically, so we have the DRAM complex up here. And below it is the dual complex, which is connected by the co-differentials. And basically, we can always be at some position along the DRAM complex, and then to the right and to the left, we have some operators, for instance, if we're here, and then these compose to generate a Hodge-Laplacian. We have different boundary conditions, so basically the first one is scalar Neumann, the last one is scalar Dirichlet, and in between we get some vector Laplacians with different boundary conditions. Now we want to transition to a weak variational form. So for this, we just take our Hodge-Laplacian and form the L2 inner product with some test function. And then we basically use this adjoint property or integration by parts. But let's say we're on a closed manifold. And then we can basically move over the left part of both compositions to the other side of the inner product and get this symmetric bilinear form. So this lets us arrive at this basically variational formulation. involving some Sobolev spaces. And the Sobolev spaces we have here are a Sobolev space which has the exterior derivative square integrable and one that has the codifferential square integrable. This is because both of them appear in the formulation. In R3, for instance, we can look at the one for the exterior derivative. This just gives rise to the various space along the de Rham complex, H grad, H curl, H diff, and L2. And now we basically get to the complication of the whole field of finite element exterior calculus, if you want so, which is that the Hodge-Laplacian has a big kernel. It is singular, and therefore it is not just invertible and doesn't have unconditional existence and uniqueness. Or in variational terms, our bilinear form is not coercive on our Sobolev space, so we cannot apply Lax-Milgram. This kernel of the Hodge-Laplacian is exactly defined basically by harmonic forms. Harmonic forms, well, their name is inspired from harmonic functions, whose Laplacian is 0. Here the Hodge-Laplacian is 0. And there's a theorem from Hodge that basically says that the space of harmonic forms is isomorphic to the de Rham cohomology. So this is basically how homology enters the picture. Turns out that basically for each, so homology is the study of holes basically of some topological space, and basically we get one harmonic function for each hole of the space, okay? A harmonic K form for a K-dimensional hole. And somehow we kind of need to care about topology because the topology determines the kernel of our PDE operator. So just to restate what de Rham cohomology is about, so we have our de Rham complex connecting the different differential form spaces with the exterior derivative, and we have our complex property that applying the exterior derivative twice gives 0, and this basically is a statement that all exact forms, so all forms that are in the image of some of the differential of the exterior derivative, will be closed, so have 0 exterior derivative themselves. But the other direction is not necessarily true. Not all closed forms are exact, and the failures of this are exactly, basically, witnesses of the holes of the domain. We can define the de Rham cohomology group, which is this quotient group between the closed and exact forms. And de Rham basically proved that the cohomology of the differential forms is actually isomorphic to the homology of the topology, so it really does represent the holes. And now, to fix this kernel issue, we need to somehow we basically invoke the Fredholm alternative, which tells us that the existence of the solution is conditionally given if and only if our source term f is orthogonal to the kernel of the Hodge-Laplacian, so to the harmonic forms. And the uniqueness is only given up to the harmonic forms. One possible fix that mathematicians like is quotient spaces to get the uniqueness, the uniqueness. And for existence, we can just basically, since we want to accept arbitrary f's, we just project out the harmonic forms, take off the harmonic part, and then we do have existence. But this is, for implementing, this is not the optimal way because it's hard to work with equivalence classes. So we look at a different fix. This is basically imposing some gauge condition. So we just say we single out a specific representative of each equivalence class of the quotient space. And the gauge is just that we want to find the U that is orthogonal to harmonic forms. That's how we get uniqueness. In weak form, we basically just say that our U should be have inner product equal to 0 for any harmonic form Q. For existence, we take a bit of a more sophisticated approach, relying on the so-called Hodge decomposition. This is a fundamental statement about differential forms, saying that any differential form can always be split into an exact part, a co-exact part, and a harmonic part. Written differently, any omega can be written as d alpha plus delta b plus h, where h is harmonic. And if we compare this to our strong form of the Hodge-Laplace equation, we can notice that this d delta u plays basically the role of alpha, and this du plays the role of beta, but our h is missing. So basically we can just introduce it as well, and through the Hodge decomposition, we know that there must be some solution to this. And yeah, this is basically equivalent to removing the harmonic part of f. So this is how we get existence. We just modify our Hodge-Laplacian by a harmonic part. All in all, we get then this system, which is now well posed. We both look for u and the p, the harmonic part, have this additional part and the orthogonality, existence and uniqueness we got. But unfortunately, this is not quite easy to discretize, since it's kind of hard to find element spaces that conform to both of these Sobolev spaces at the same time. So we kind of want to get rid of one of them and just do everything in the one that uses the exterior derivative. So somehow we need to eliminate the codifferential from this term. We do this by switching to what is called a mixed formulation. This is an idea for classical finite element theory. We introduce this sigma as the codifferential of u, and we basically enforce this weakly by stating this. So we have some test function tau, and yeah, this is a weak enforcement of this codifferential. And then we can basically use the adjoint condition again to move the codifferential to the test function where it becomes an exterior derivative. And now our bilinear form, we can replace delta u by sigma, and now the other codifferential, we also use the adjoint property and move it to the other side, also becoming an exterior derivative. So all in all, we only now have exterior derivatives. And now we arrive at the final form of our variational problem for the Hodge-Laplacian. We first have the weak codifferential of u enforced in the first equation. We have our weak Hodge decomposition of f, and then we have this orthogonality gauge constraint. And this is some saddle point system. We also have existence and uniqueness by some inf sub condition, and yes, now we're basically ready to discretize. And so we start by taking our manifold, and we somehow need to turn it into a mesh. The atoms or the elements of our mesh are called simplices. In 2D, these are triangles. In 3D, we have tetrahedron. And in general, they're always like the convex hull of some k+1 points. This is a geometric definition relying on coordinates. To be more in line with differential geometry, we try to separate topology and geometry. So we don't want to use the coordinates in our simplex definition, but instead rely basically on abstract combinatorial k-simplices, just by basically numbering through all the vertices in the mesh. And then the simplices are just lists of numbers of these vertex indices. And this is then just combinatorial. And simplices basically always have two orientations, positive and negative. Here in the abstract case, this is basically the two equivalence classes of even and odd permutations. The most important operator on a simplex is the boundary operator. It gives us simplices of one dimension lower that are signed, and it basically does what it says. It gives us the boundary. So if we take some edge and compute its boundary, we get the two endpoints, the two vertices signed. So there is some direction. For the triangle, we get three parts. We can absorb the minus sign and swap these two, and then basically we see that these edges really do provide a consistent orientation path along the triangle. The most important property here is that the boundary operator applied twice is 0. And this hopefully reminds you somewhat of the exterior derivative. We will see what's up with this. So basically, to define our mesh, we can start with top-level simplices, for instance, in 3D with tetrahedron, but in fact, we need all the sub-simplices as well. So basically, we can start with our top-level simplices and apply the boundary operator recursively, generating basically all the sub-simplices. So the tetrahedrons have faces, which are triangles. Those have edges, and then these have vertices. And all of these simplices together form then the simplicial complex. We can now basically define a vector space of simplices by allowing formal linear combinations of them. And these are then called K-chains. So K-chains are linear combinations of the K-simplices of the mesh. And turns out that these vector spaces form a complex. This is a complex in the same sense that the de Rham complex is a complex. It has some complex property, which here is the boundary operator, and basically the arrows are in the other direction compared to differential forms. But you can do homology on this. And here, this is really closer to the actual topology, because here we really kind of define what it means for a topological space to have a hole. Anything that is a boundary is always a cycle. So a boundary doesn't have a boundary itself, because boundaries are always closed. But the other way around is not necessarily true. Not everything that is a cycle that is closed necessarily is the boundary of something else. This fails exactly then when there is a hole and you cannot put anything whose boundary it should be. We also have a homology group, and yeah, this is basically so computationally, to compute this boundary operator is very simple. You have your data structure that basically has all your simplices, and then this is just basically a signed incidence matrix, where you check if one simplex is the subsimplex of another. You check the relative orientation, and this gives you the sign, and if they're not incident, you get a 0. So this is basically the computational representation of the boundary operator. And now what's left to do? Now basically topology is finished. We can introduce some geometry. Initially, we remove the coordinates for the simplices. We could now use separately an embedding, but this is not what we want to do, because we want to do geometry intrinsically. And so instead we just use a Riemannian metric that's defined on the simplices. The benefit from this is hopefully to easily mesh abstract manifolds, like a flat torus that has just periodic boundary conditions, or a Klein bottle. And what one could do is extend this naturally to pseudo-Riemannian geometries, where your metric is, where you have a Lorentzian metric, and you could do FEEC on 4D spacetime. So the metric on the simplex is pretty simple. Simplices are flat. If you imagine a triangle, it's flat. And so therefore the metric is constant inside of the simplices. And then globally over the whole mesh, the metric is piecewise constant. And we can computationally represent this metric on a simplex using a matrix as a Gram matrix by picking some bases. One possible basis that's particularly simple is to take vertex 0 and look at all the vectors emanating from it to all other vertices. And if you then compute the dot products between them, this is what would give rise to this Gram matrix. An equivalent description for this would be edge lengths instead of, so edge lengths are basically just numbers that describe what's the distance between two pairs of vertices. This is completely agnostic of the embedding, and it turns out this is completely equivalent to the metric, and you can compute both from each other. Okay, we're finished with the mesh. We got topology and geometry defined. Now we can get to the actual differential forms. These discrete differential forms come basically in two flavors. One being simplicial cochains and the other being Whitney forms. And they come in pairs. The cochains are really the primary discrete objects. They're not differential forms in the original sense. They're a completely different object. They're basically just functions on the simplices. And so they're basically computation just list of numbers. But you can compute the discrete exterior derivative on them. The other side of the story are Whitney forms. They are basically the differential forms, the proper one you can reconstruct from the cochains. And the Whitney basis is then our finite element basis functions. So let's start with simplicial cochains. So basically, this is a rather simple concept, to be honest. You basically just you have real value functions on the k-simplices. So basically, a differential k form becomes in the discrete setting just a list of number where you have a number associated with each simplex. The meaning of this can be best understood if you look at the discretization map, the RAM map, which basically takes in some continuous differential form, turns it into a cochain. And this is done by just taking the original differential form and integrating it separately over each simplex, where we always obtain one value, and this value is the cochain value. These cochains have a very similar name to chains, and this is because they're dual. So we've seen chains before. These are this linear combination of the k-simplices, and we have cochains that are linear functionals on the k-chains. The chains have a subscript and the cochains have an upper script. And basically, the chains are basically the domains you integrate over, right? So multiple simplices. And the cochains are your discrete differential forms, so they're like the analytic things you do integrate. And they have different operators active. We have the boundary on chains and the discrete exterior derivative on the cochains, and you could do homology on the chains and cohomology on the cochains. The thing that pairs them up is the duality pairing. And basically the meaning of this duality pairing is basically to figure out what the integral of your discrete exterior, the discrete differential form would be over some chain. So you pair up your cochain and your chain and you get the value of the integral. Using this, we can define the discrete exterior derivative. We start with Stokes' theorem, relating the exterior derivative and the boundary operator, and then you basically can re-express this in the duality pairing as this statement. And here you can see that the exterior derivative is the adjoint of the boundary operator. Computationally, this really just means that our discrete exterior derivative is a matrix which is the transpose of the signed incidence matrix. And here you can again appreciate how the exterior derivative, also in the discrete setting, is purely topological. It just uses the incidence relations. The other side of the stories are these Whitney forms. They are our finite dimensional subspaces of the Sobolev space and basically unify the different finite element spaces from classical FEM. The zero Whitney forms are the Lagrangian nodal basis. The n forms are the piecewise constant functions. And in between you have more exotic ones, the Nedelec and Ravia-Thomas elements, which are used for vector problems. Let's start with the basis. So we've seen that the cochains have one value for each k-simplex. Here it's similar. Whitney forms have one basis functions for each k-simplex as well. And so, yeah, the basis functions for a Whitney K-form live on all K-simplices. And these Whitney bases fulfill some basis property that is quite elegant, that if we integrate this basis function over its corresponding simplex, we get unity with a sign depending on the orientation, and 0 otherwise if they don't correspond. If we now restrict the basis function to one top-level simplex, there's some formula in terms of barycentric coordinate functions to compute this local shape function. And we can visualize these, for instance, on the reference triangle. So these are the Whitney 1 forms. 1 forms are associated with edges because they're one-dimensional. And so we have one function that is associated with this edge, one that's associated with this one, and one that's associated with this one. We can then look at the global shape functions. Edges are adjacent to 2 triangles, so the support of the basis function is over 2. And then by doing linear combinations of these global shape functions, we can get whole fields, so actual Whitney forms, divergent fields or rotational fields, yeah. And this is actually where the reconstruction map comes back into play. As I said, there's one basis function per simplex. There's one cochain value per simplex. Well, these cochain values are the coefficients in the linear combinations of basis functions. And this is exactly what the reconstruction map, the Whitney map, must do. It takes a cochain and maps it to a Whitney form by just computing this basis expansion. These de Rham map or Whitney maps are basically kind of not quite inverses, but they basically do the opposites of each other. One does discretization by integrating, and the one does reconstruction by using the Whitney basis functions. And these fulfill a so-called cochain map property, where they commute with the exterior derivative. And this really now makes everything work, or makes this construction work, because now our complexes basically are isomorphic to each other, where our de Rham complex, this is a commutative diagram that shows that basically it doesn't matter if you first integrate and then take the exterior derivative, or integrate and then take the Whitney map and then differentiate. It's all the same. So these are isomorphic, have the same cohomology, and yeah, this is really the structural preservation we've been aiming at. Or in other words, if you combine both of these maps in this way, you get a projection operator from arbitrary differential forms down to Whitney forms, and this also commutes with the exterior derivative, and this shows us that the Whitney complex really is a subcomplex of the de Rham complex. Let's look at the Galerkin discretization of our variational problem. We just replace our Sobolev space with the Whitney space, and basically, as I said, we get convergence guaranteed by this projection operator, and we get basically first order convergence. We can now use our basis expansions, pull out the coefficients out of the bilinear forms. These coefficients are actually cochain values, and then rewrite everything with matrices. And this is really the linear system that I'm solving in my library then. And so the only things that really appear here are the discrete exterior derivative. We've seen this is just the transpose of the signed incidence matrix. Quite straightforward. Then there is this matrix M, that's the mass matrix. This is really the only Galerkin matrix you need to assemble. We'll do this next. And then there are also the harmonic forms expressed in the Whitney basis. So this is, you kind of need to pre-compute the harmonic forms in order to solve the source problem. This mass matrix, as I said, is the only Galerkin matrix you need to compute. It's just the matrix filled with all the L2 inner products of all Whitney basis functions with each other. And if you look at the local math matrix and use the Whitney local shape functions and expand its definition, then you can rearrange, and this is basically the expression you arrive at. This is a constant term because derivatives of barycentric coordinate functions are constant, and then there's only this integral left of two barycentric coordinate functions for which an analytic solution is known, so all of this can be done analytically, no quadrature needed. This basically completes the whole construction. So my library is then capable of solving Hodge-Laplace problems, eigenvalue problems, and source problems, basically on any mesh of any dimension, any topology. And I want to look at a few results. Here, for instance, we have the torus, and we try to compute the harmonic one-forms. And the torus basically has two one-dimensional holes, one obvious one you can all see, and another one that goes along the rim basically. Since this is hollow, there's a second one-dimensional hole here inside. And so, since there are two holes, there must be two harmonic one-forms, and these are here visualized as vector fields. They're perpendicular to it and span this space of harmonic forms. I can also do this on some other mesh, really any mesh works, but it's kind of hard to visualize any high-dimensional manifold, so really only two-dimensional ones really work well. And yeah, this is basically it. So to summarize, FEEC tries to kind of combine these three mathematical frameworks of differential geometry, algebraic topology, and functional analysis. And basically, then I use these frameworks in my library to create just a very general library that works coordinate-free, arbitrary differential form degrees, but only first-order Whitney forms. Yeah. Possible extensions would be to use higher polynomial degree basis functions. There exist arbitrary degree basis functions, in fact, but I only use the lowest degree. And it would be interesting to try to solve some problems in Lorentzian geometry in 4D spacetime. And of course, solve other PDEs like Maxwell or something similar. Yeah. Thank you so much. Yeah?
Have a question for the saddle point system or the dimension. So initially we had the elliptic problem, and then because of this geometric constraint, it becomes a saddle point. So I can think of this Gauge condition like in classical simulation, like the Lagrange kind of constraint to impose like object. Okay.
Yeah, this is basically a Lagrange multiplier, if I understand it correctly. The problem with the saddle point problem is more from the mixed formulation, because you introduce this auxiliary variable more than this Lagrange multiplier. It's kind of independent. Yes?
Does your implementation, because maybe I misunderstood or missed it, but when you want to do, let's say you have a manifold that's actually curved, in your case the superficial mesh afterwards does it contain the curvature as well?
This is one part of the theory that is needed. It is Reggie calculus. It's this idea of trying to of using these edge lengths to represent the curvature of the manifold. Of course, this manifold is in its approximation and somehow piecewise flat, but you get in Reggie calculus, they say basically that the curvature is concentrated on the codimension 2 skeleton. So if you imagine you have so codimension 2 means if you have 2D triangles, these are codimension, so the triangles themselves codimension 0, this is codimension 1, the vertices are codimension 0, and this is where the curvature lives. Because what you can do is, you can compute the angles here, right, with your metric on each simplex, and if they add up to more or less than 360 around the vertex, well then there must be some curvature. Right, so it is represented in these edge lengths.
Okay.
This does work. Yes.
And you mentioned as an extension that you want to add an axial. Just for us to maybe recap the course of it, what would you need to add to your current implementation?
Good question. So I think the probably easiest extension would be to use, if you do a time harmonic sourceless problem, you basically get a curl-curl equation. And so this is just 1/2 of the Hodge-Laplacian. So I think this would be rather straightforward. If you want to sort of like full Maxwell, I feel like you need to somehow think about the Dirac operator or something. I don't quite know what this entails, but surely would be interesting. And I guess it would make sense to do it in a relativistic formulation on Minkowski space or something. Yes.
Yeah, super cool.
Maybe I can comment on that. Yeah, if you do time, well, we talk about after the break anyway on that. But if you do time stepping, then you just need to increase the dimension by 1 and that's it. Because this flavor would then, well, and you have to change the signature of the metric. Yeah. But if you do that, yeah, so you have to admit like negative, the edge length of your triangles would be negative in the time direction. Yeah. And if you do that and you use a 4D mesh, yeah, then you are done because that is exactly the correct structures that we need here. Of course, I mean, if you want to solve the initial value problem, then you would maybe start on a 3D plane, kind of. And then this mesh would grow in the time direction. And that is then the geometric representation of what you think about time stepping or time integration. So one would probably not have a fixed mesh once and for all that covers the whole time range, yeah, but I have seen discretizations like that as well. So in a way, the answer to your question, what needs to be extended, yeah, if I'm a bit bold, I would say nothing, yeah, it's already in practice. Yeah.
Any other questions? Otherwise, you can always come to me afterwards.
I have a remark which goes in the same direction in your first question. Can you bring up this slide in the settle point formulation again, please?
Does this suffice?
There is, it's not shown.
It's not shown.
Yeah, that's good. Thank you. Yeah. So, if we for a moment just think of a trivial topology, then we can forget this last equation, right? Yeah, because that is just to fix the contribution that comes from the cohomology. And if the topology is trivial, yeah, there is no such contribution. And then one could also think of that second equation. That's like in the core, this curl-curl type of with du, dv, yeah, that's very similar to what I wrote at the board at the beginning. And then add the gauge weakly with the help of a Lagrange multiplier. Then you would write the first equation, that's like the weak gauge, yeah, and then this extra condition is then added with the help of the Lagrange multiplier, and then the sigma would play here the role of the Lagrange multiplier. Yeah. So that's just like telling your story the other way around. You started with a Hodge and say, oh, bad, yeah, I have this co-derivative. That's hard to discretize. So let's think of a way of getting rid of this co-derivative. Yeah, and then you arrive at that settle point problem. One could also say, yeah, let's start from the curl-curl type of, and then make it unique by adding a gauge. Unfortunately, this gauge is not easy to handle on your discrete space, yeah, so let's add it weakly by using a Lagrange multiplier, and that's the same story. I have a last remark. If you go to the discrete version of that, you had a matrix version last, yeah. Yes, this one, because one could in principle derive, a student of mine did that with probabilistic stuff, yeah, so he has actually good reason to do that. We could actually eliminate the Lagrange multiplier here on the discrete level. I could solve the first equation for sigma, and then plug this first equation solved for sigma into the second equation, and forget about the harmonic part. Now, question to the audience, why is this a bad idea in the FEM context? Analytically, I can do that, there is no trick, you don't lose uniqueness, you just, that's like a block solve. You have a large system and we use a block solve for the first equation, solve it for sigma, plug it into the second equation. But FEM guys would never do that. Any idea why?
Did we maybe rule sparsity?
Yes, because these mass matrices are, as Louis pointed out, are sparse. They are just like interaction of local Whitney shape functions. So they are very sparse, and if you have different simplices that do not overlap, you get zero. Unfortunately, the inverse of these matrices are in general dense. So you can do that formally, but you destroy the sparseness of your system, and that is of course something that you won't like to have in a numerical solution. There you'd rather stick with the saddle point problem and solve it exactly the way you wrote it down. Maybe one last thing and then I stop talking. If you think about Maxwell's equation, say divergence free law, that's the simplest one, dB equals 0. How many elements do you need to discretize that in his setting exactly? 10 or 100, or what would you recommend to engineer? I'm not talking about the whole Maxwell system, but just a single equation, dB equals 0. Then Louis comes and says, no problem, that's a two-form. So I use a subspace of these Whitney two forms that would be like phase-based elements, where the degrees of freedom would be the fluxes of these B-fields through the phases. And then I would go to this discrete subspace and plug that in and then see, okay, now the discrete space, what happens to this equation dB equals 0? That is actually, in Deutsch would man sagen, Fangfrage.
I would say something like that, well, it doesn't matter, it's anyways instantly fulfilled as soon as you have any mesh.
You showed that the discretization, the projector into the Whitney space, commutes with the exterior derivative. So that means, as you explained it, if I first take the exterior derivative and then go to the discrete subspace, I get the same result as if I first go to the subspace and then take the exterior derivative. And if you apply that to dB equals 0, then you see that in your subspace, also dB equals 0 on the discrete level holds exactly. And the discretization does not enter at all. And this is because the exterior derivative is a differential topological operator that does not feel metric, but just stuff like holds, like connectivities and so on, and you exactly reproduce it on the discrete level. So one element will do. So if Maxwell consisted only of dB equals 0, that would be a simple job to come up with all the things like refinement and everything that comes through the metric. So the devil is in your L2 products, and not in the exterior derivative. And when I was a student, I thought curl is bad, and material laws are good because they are simple. Meanwhile, I realized it's the other way around. The exterior derivative is good, and the L2 is bad.
Great.
Thank you.
Thank you.